Pt.1. So today we're going to do 12.5. We'll also get to 12.6. 12.5 is on lines and planes. So this is neat up until now when we deal with lines in two-dimensional space. We describe the line something like that, right? You're going to notice we describe it totally differently when you go to three-dimensional space, but it's not challenging at all. So I'm going to use this design right here. Y equals mx plus b. Yeah, that's great in two-dimensional space, but what about in three-dimensional space? How can you describe a line and all the points on a line? So we use vectors to do that. Isn't that cool? We actually use vectors. So I drew an image here, and this is the x-axis, the y-axis. We can then apply this to three-dimensional space using the vectors. Using the triangle law, I've got initial r here, r sub 0 or r naught. I got some vector A that's right on the line. Everyone see that? And I got a vector just r. So let's just talk about r, because that would be like the tip of this. And using that, you could describe any point along this line. You can keep stemming like another r along this line. So I'm going to start out by writing the triangle law. And then we'll generate the equation of how we can deal with lines, and it'll be real easy. Let me start with this. Do you agree by the triangle law that vector r sub 0 plus the vector A equals vector r, right? Mm-hmm. In fact, I'll write it as r equals this vector plus. This is going to allow us to create an equation of lines, not only for two space, but three space, using vectors. Vectors are so cool. All right, what I'm going to do is I'm going to think of a vector that's parallel to the line. That's the secret. I'm just going to take, I've got a vector right here. Let's call it vector v. And I'm just going to put v right there. And let's just make a note, everyone. Vector v is parallel to the line. Okay?
Oh, which line?
To that line L right there.
Okay.
And I just drew a vector v, and when I put it off the origin, I could have put it anywhere, but I just wrote it on the board, and I said, let's just refer to some vector v that's parallel to the line. This is the secret to how we can deal with this scenario. And what we're doing is that when we are deriving what would be the equation for a line, but not just two space, you can use it two space, but three space. Now, vector v and vector a are parallel. You all agree? So, can I replace vector a with vector v? I can, as long as I think of it as a scalar multiple of this. So what I'm going to do is I'm going to replace a with just vector v times some scalar multiple. Just a variable. And I'm going to use the variable t. Alright? I'm going to use the variable t. So I'm just going to be like, right here, how about b times t? And this is what we got. We can actually describe any line with a vector, where this right here will be just some point. I know it's written like a vector right here, but this will be some initial point on the line. Alright? I can take the t and just factor it out of this vector, and this vector v here will be the parallel vector. Boy, this is how we can describe any line. And if you want, what variable did I use? T. You can think of this as a vector equation, like just r. If you want, you can call it r of t, as if everything's going to be in terms of the variable t. We'll always use t as our, you might say variable. Let's call it a parameter. Let's call it a parameter because we already got what letters? X, Y, and what's the other letter? Z. So we'll x, y, and z, we'll say those are the variables representing points in three-dimensional space. We've got a new letter t, and we'll just call that the parameter. That's our parameter. But we can describe any line like this. So all you'll need is a point on a line, just one point. I wrote initial, it could be any point on the line, and you need a parallel vector. Alright, so we'll start with a simple example. The key is to describe any line in three-dimensional space from here on out. You need a point on a line, just one, but you also need a vector that is parallel to the line. Sound cool? So you might not think of it like this, although this is really what it is. This right here is just that initial point. You can think of it as like, you know, if it's the point 1, 2, 3, and you can write it as a vector if you want, because it's like it'd be the vector that went from there, from the point, from the origin, right? If you subtract 1, 2, 3 minus 0, 0, 0, tip minus tail, you'd still get the what? 1, 2, 3.
Point vector.
So I'm going to keep this here, erase everything else, and let's play with this. So here's a point on a line. It's the point 1, 2, 3. This vector is parallel to your line. Four, 5, 6. And I want you to come up with the parametric equations of the line. We don't have to write it as a vector. All right? If you want, you can. For lines, you can say R of t is equals R sub 0 plus t times vector b parallel vector. But here's another way to think of it. The three parametric equations. So what I'm going to do, I'm going to come up with this. These are called the parametric equations of the line. And there's not a typo here. There's not a typo here. I didn't say equation, I said parametric equations. So if we want to talk about describing that line, because we have this parameter t, we'll talk about what's x equal to, what's y equal to, and what's z equal to. Alright? I'll start by writing it as a vector, then we can write it this way. So, I'm going to do this. Write it as a vector. And what would be the vector equation of the line? The vector equation of the line, I'll erase this. Is simply here. R of t equals initial point plus t times parallel vector. What's the initial point? 1, 2, 3. I'll write it as a vector. Plus parameter t, and what's the parallel vector? 4, 5, 6. Put a big box around this. You gotta love this. We will not make this too complicated. Take all this out of the way. We can keep that up there. But this is the vector equation of that line. RT equals 1, 2, 3 plus parameter t times 4, 5, 6. But can we combine these to make one vector? So let's do that. What would be in the x component? See, this is x, this is y, this is z. 1 plus 4t, or 4t plus 1. What's in this y component? 2 plus 5t. And the third component? 3 plus 6t. And that's the vector equation of the line. But I'm going to come back to this. A lot of times in our course, you may just want to write the three parametric equations of the line. Well then, what can I say x is equal to? X is equal to the what? 1 plus 4t. The y is the 2 plus 5t. The z is the 3 plus 6t. If you're just asked to describe the line or come up with the line, everyone, of course, you can write it as a vector. If you're just like, I got to come up with that line. But sometimes you'll notice the directions are just specific. And we'll say, write the parametric equations of the line. Then he wants you to write them like this. You can write them vertically. You can write them horizontally. If you write them horizontally, you might want to put commas between them, right? Because you'll have those three parametric equations of the line. But please, feel free to write these lines as a vector. All right. The next section after 12.6 is vector functions, right? And that's exactly how you describe a line with a vector function. It'll look something like this. There won't be any t-squareds in there, right? You start trying to describe some curve in three-dimensional space, okay, that's probably going to have maybe a t squared or a t cubed. It's straight lines, just 1 plus 4t, 2 plus 5t, and 3 plus 6t. Most importantly, hidden in here, or hidden in here, where are the components that made the parallel vector? I wanted to make sure you know where that was. Those are the numbers in front of what parameter? T. That's the parallel vector.
You also said that, right?
What's that?
You also said it on the question, that which is the parallel.
That's right. In this problem, they just gave it to you. So he's like, man, this one was easy. They gave us the parallel vector. They gave us the point on line. So let's go to another problem. And when you can write it as a vector, or you can write the parametric equations of a line. Can I erase this? But at least this is always going to be there, right? Throughout our whole course, the parallel vector goes in front of those t's. What goes here? Just the what?
Initial point.
The 1 point. Yeah, just the point. So you can write it like this, but you can also write it like, in this case, if you prefer, or you can write it as a vector. But it's coordinated in the directions, right? I know in this section, you'll notice the directions, they'll say, find the parametric equations of the line. Then the next problem, they go, find the vector equation of the line. And you can write it either way. All right, so now, let's try another one. I'll erase all this. One, 2, 5, 3, 4, 6. These are 2 points. Question? Find the line that represents those 2 points. Hey, be more specific. Okay, how about this? Find the parametric equations of a line that goes to these 2 points. So once again, what do I need when it comes to lines? I need a point, right?
Point and a vector.
And what kind of vector do I need?
Parallel.
So that's the challenge in this problem. So we're going to need you to brainstorm. I need a point on a line. Gosh, we got 2 of them, right? I always pick the first one. Is that one okay with that? I always do. Up through chapter 16, they give you 2 points. Let's pick the first one. All right, 1, 2, 5. 1, 2, 5. Now I'm stuck. So I'm just thinking, let's draw a picture. Sometimes drawing a picture helps us figure this out. This is some point 1, 2, 5. This is some point 3, 4, 6. And I have to come up with the parametric equations of the line. You know, don't you?
Can't you just do tip minus tail and then multiply it by something?
She found a parallel vector. The challenge here was just to find that what? We just need the parallel vector. All they gave us was 2 points. And she says, well, if you just do tip minus tail, you will find a vector right on this line. In fact, parallel to the line, right?
Mm-hmm.
I mean, it's right on a line, but it's running in the same direction as this line here, parallel to the line. True? So if they give you 2 points, you can always use the vector tip minus tail between those 2 points. So what is, here I'll put a vector right there. There it is. She says use that vector. That's your parallel vector. So cool. What's 3 minus 1? Alright, so tip minus tail, 3 minus 1 is 2. 4 minus 2? 6 minus 5. 1. And I should have at least got some negatives in there, huh? Sorry about that. We get negatives, we understand that. There's a parametric equation of the line. Can you write that as a vector? Certainly, that's the parametric. They ask for the parametric equations. I write them vertically, you can write them horizontally. And just put commas between them. What's the vector equation of the line? One each just R of t?
RT,
Alright,
then
yeah. 1, 2, 5 plus t times 2, 2, 1. Just remember, where is that parallel vector going? With the parameter, right? We derived it that way. Or what's another way? Most students like to write it as one x, y, and z component, like here. What's here? 1 plus 2t, 2 plus 2t, and what's the last part? 5 plus 2.
so the bottom part we call it like a vector equation of the line, and that one is parametric equation of the line, right?
Exactly. I'll repeat that. Very good. This is the vector equation of the line. Either one of these. Both of these are fine. These are the parametric equations of the line. Parametric because we're using this parameter t. Alright? We can always use the parameter t when describing lines. So throughout this whole course, you can imagine we got a lot of lines. Ooh, a beam of light, like going like this. So a lot of lines in this course, you can easily recognize them in later chapters because it won't have any t squareds, won't have any t cubes, it won't have any sine of t's or cosine of t's or e to the t's. It's just going to be like